Okay, so this is our final section in Chapter 5. This is 5.8, and we're going to be solving quadratic, but not equations, quadratic inequalities. Okay, it's not too bad. I try to make everything, at least in this section, because the inequality part is new. I try to make the quadratics themselves a little bit easier to factor and whatnot. The most important thing you have to see is what to do a little bit after you do the stuff that's familiar to you. So here's what I mean. If you look at the first example in your notes, example 1, it's x squared minus 3x is less than or equal to 18. Now, this is starting to look like something we saw a little bit earlier in the chapter. If I had an equal sign in place of the less than or equal to sign, what we would probably do is we would bring everything to one side. So we'd subtract the 18. And then if we look at the left-hand side of this inequality, oops, I just made it that you can't see it. But if you look at that left-hand side, you would notice that it's factorable. It was x squared minus 3x minus 18. So let's try to factor it. Let's think of two things that multiply to negative 18 and add to negative 3. Hopefully you're thinking a little bit on your own. That's why I'm pausing before I give it away. Hopefully you thought of minus 6 and positive 3. So those are the factors of x squared minus 3x minus 18. Now I'm going to solve each of these factors for 0. So at this point it's very similar to what we've done in the past. So the first factor is x equals 6. The second factor is x equals negative 3. So I got the two values that make x exactly 0. Now I want to try to figure out where x is less than or equal to 0, because that's the point of the problem. So here's how I do that to help me analyze my answer. I draw a number line, which should make sense to you. Almost every time we've dealt with an inequality this year, we've used a number line to express what's going on. Okay, I'll put 0 in the middle, I'll put 6 over there, I'll put negative 3 to the left of 0 where it belongs. Now, at 6 and negative 3, I get exactly 0. Since the inequality is less than or equal to 0, I'm going to shade, or rather put dots at 6 and negative 3 to prove that they are a solution. Now what I'm going to do is I'm going to test one point in each of three regions. The region to the right of 6, the region between 3 and 6, and the region to the left of negative 3. Okay? So when x is more than 6, let's pick something like 7. I'm going to plug that back into the factored form and see if I get a product that is less than 0. All right, so 7 minus 6 is 1. 7 plus 3 is 10. Well, 1 times 10 is not less than 0. It's bigger than 0. So this region is false. I'll pick something in between negative 3 and 6 now. I'll choose 0. So 0 minus 6 is negative 6. 0 plus 3 is 3. We multiply that together, we get negative 18. That is indeed less than or equal to 0. So that means not only is 0 a solution, but everything in between negative 3 and positive 6 is a solution. Now let's just test things less than negative 3, so why don't we do something like negative 5. Negative 5 minus 6 is negative 11. Negative 5 plus 3 is negative 2. That multiplies to a positive 22. So everything to the left of negative 3 has to also be false. So we can now say that our solution set is the set of all x's such that x is greater than or equal to negative 3, but also less than or equal to positive 6. Okay? We have to do that kind of analysis because of the fact that it's a quadratic as opposed to a linear inequality. Okay, we don't really have an or an and guarantee here the way we did with linear examples. So that's basically what you're going to do. We'll do another one, and then I'll let you try a couple on your own. So if we look at the second example, we've got x squared minus 14x is greater than negative 49. So again, we're going to start like we've done. We're going to bring the 49 over and basically treat this like an equation. Okay. Now we need to come up with two numbers that multiply to positive 49 but add to negative 14. All right, well, this is a perfect square. It's x minus 7 and x minus 7. Okay, so this time there's only going to be one of these critical values that makes the expression exactly 0, and that's going to be at x equals 7, because we said x minus 7 equal to 0, and we get that x equals 7. All right, so we go to our number line. We know it's 7, it's at 0. This time it's open because if you look at the inequality symbol, we want to be strictly greater than 0. So we'll pick something larger than 7, we'll pick something smaller than 7, and see what happens. Okay, so if we pick something like, I don't know, positive 10, we get 10 minus 7 is 3. 10 minus 7 is 3. That's a positive 9. So these are all positive. So everything bigger than 7 is going to work for this inequality. Let's try something smaller than 7. Let's use 0. So we get negative 7 times negative 7. It's going to be positive 49. So guess what? Everything less than 7 works as well. This is a weird one. We've never seen an inequality like this. So let me show you the set notation for that, how you would write it. You would say the set of all x such that x is a real number. Remember, this is an element of reals, comma, x does not equal 7. So basically what we're saying here is the solution to this inequality is any real number under the sun except the number 7. Because the number 7 gets you exactly 0, and we want to be greater than 0. Okay? How about we do just one more? Okay, so for a third example, let's do x squared plus 7x is greater than or equal to negative 10. Okay, so again, we're going to start this just like it's an equation. We're really not going to deal with the inequality symbol until the very end of the problem when we analyze it on the number line. So we'll bring that negative 10 to the left, and then we'll factor and solve. So two numbers that multiply to positive 10 and add to positive 7, positive 5 and positive 2. So we set each of these factors to 0. We get that x has to be negative 2 and negative 5. So they will be our critical values on our number line. Okay. At negative 5 and negative 2, we get exactly 0. So we're going to have dots at those points because we're allowed to be exactly 0 because of the bar on the inequality symbol. So now we've got some regions to check. We've got to check a number greater than 2, a number in between negative 2 and negative 5, and then a number less than negative 5. Okay, so let's do that. Let's use 0. 0 plus 5 is 5. 0 plus 2 is 2. 5 times 2 is 10, which is positive. So it's going to be positive here, so everything greater than negative 2 has to work. Okay, let's try something in between negative 5 and negative 2. Why don't we use, I don't know, negative 4. So negative 4 plus 5 is positive 1. Negative 4 plus 2 is negative 2. They multiply to get negative 2, so this is negative. So anything in between negative 5 and negative 2 is going to give us a negative value for this inequality, so it's not a true solution. Now we'll pick something less than negative 5. Let's use, I don't know, negative 10. So negative 10 plus 5 is negative 5. Negative 10 plus 2 is negative 8. They multiply to get positive 40, so that's positive. So we've got a winner for everything less than negative 5. So our solution set is the set of all x such that x is greater than or equal to negative 2. That's for this first region. Or x is less than or equal to negative 5. And that corresponds with this region here that we shaded. Okay? You have a couple example problems to try in the notes. Please do that. Bring any questions you have to class. And with that, I wish you a good evening.